In this video, we are going to discuss solids of revolution, and we're going to find the volume of a solid of revolution using what's called the disk method, or similarly the washer method. They're very closely related methods. So we're going to start off with an example, and then I'm going to walk you through the method, and then we're going to apply it to a couple of different problems. So let's start with this first one. It says, let R be the region bounded by y equals 2.5 plus sine of x equals 0, x equals 2 pi, and the horizontal line y equals -1. Find the volume of the solid of revolution formed by, shouldn't say rotating, revolving the region R about the line y equals -1. So the first thing you want to do with solid of revolution problems is sketch the region. Always, always, always sketch this. Now we have y equals -1, that's a horizontal line, that's down here. So that's one bound. X equals 0 is also the y-axis, so that's another bound. X equals 2 pi, it's going to be over here. It's another bound. And y equals 2.5 plus sine of x, remember how that looks. Sine of x oscillates between -1 and 1. So it starts at 0, then it goes up to 1, then it goes down to 0, then back down to -1, and then back up to 0. So it has this little wave in it. So we're going to take that wave and we're going to shift it up 2.5 units. So instead of being centered at 0, 0, or instead of being centered at y equals 0 on that line, it's going to be centered on the line y equals 2.5. So this is the center line for that. Now that line has absolutely nothing to do with our solid, these other lines do. I'm just using this to have to identify my center line. And if y equals 2.5 plus sine of x, we're going to go from on the center line, start on the center line, then we're going to go up 1 unit to 3.5, and then back to the center line, and then down 1 unit to 2.5, and then back to the center line. So we're seeing something that looks like this. Now the region is bounded by this line, and this line. So it's actually this whole thing. All the way down here. That is our region. And we're told that we are revolving this about the line y equals -1. And you see about the line. Y equals a constant is a horizontal line. So we're right here. And we're taking this region and we're revolving it about this line. So I'm going to put an arrow there just to remind myself. Now, it's hard to draw, but we do the best we can. I want to sketch, after I've sketched R, I want to sketch a reflection of R about the line that they told me. So in this case, I want to sketch the reflection. About y equals -1. So you have to imagine like taking this piece of paper and then like flipping it down and saying, what would that shape look like if it was flipped down? If you wanted, you could just take the paper, fold it in half, and then see what that reflection would look like and then trace. So that's an option. I want to be a little bit more precise. So I'm starting at y equals -1 and I'm going up to 2.5. So that means I need to go, it looks like 1, 2, 3 and a half units down. So I'm going to go to -2, -3, -4, that's 3 units, -5, 3.5 would be right here. And then -6 would be here. So after the reflection, this would be the new center line, and instead of going out up 1, I'm going to go down 1. And then back to center, and then up 1, and back to center. Do you see how that's the reflection? If I take that point and I reflect it down, it looks like this. If you take that point that's all the way up there, I reflect it down, it goes here. Take that one and reflect it down, it goes there. So my reflection is this blue region. It does not have to be perfect, but I'm taking this region and I'm revolving it around this axis, and this is what I would see. In 2D, I would see this face. Now, it's actually a 3D shape. It looks more like a vase. On one end, you're going to see a circle, and on the other end, you're going to see a circle. See, the radius of this circle looks like it's, well, that's 2.5 plus 1. The radius is 3.5 over here. Actually, these circles are going to have the same size. The radius is 3.5 over here. The radius is 3.5 over here. Here, the radius is going to be larger. The radius is going to change from slice to slice, but we're going to have circles. We're going to, once we take that and we rotate it around, we're going to have circular slices. So we've sketched a reflection of r about y equals -1, and then we want to slice perpendicular to the axis that we just revolved around. And the reason we slice perpendicular to that axis is so that all of our slices look like either discs or washers. So if I'm slicing perpendicular to this axis, my slice looks something like that. Or if I prefer, instead of thinking of slicing the solid perpendicular to the axis, I can think of taking my original region. That's this region up here that was in black. And I am slicing that perpendicular to the axis. I'm forming that representative rectangle. Remember that guy? So there's my representative rectangle. And imagine you take that rectangle and you rotate it around. Well, in the reflection, that rectangle is going to end up down here. But if I look at it on the side with a little bit of dimension, it's going to look like this. Now, since there's no gap between, there's no gap between this region that I rotated and my axis, the cross section is a disc. It's a little circular disc. So we slice perpendicular to the axis. You can either do a slice the original region, into a representative rectangle, into rectangles, excuse me. So we're slicing it and then we're drawing a representative rectangle. So that's one option. Or you can actually slice it into things that look like discs or washers. Now, since there was no gap in between that axis and my region, that's one solid piece. I've got discs. So notice this time we have discs. Okay, now the question becomes, how do I find the volume of that piece? Because if I can find the volume of that piece, I can find the volume of the entire solid of revolution. Well, we do exactly the same thing we did in the previous section, except this time they're all going to have very similar geometry. Because it's a solid of revolution, I'm going to get either a disc or a washer. And we'll see the washer case in a little bit. Since I've revolved this around, I took this rectangle and I revolved it around a circle, I'm going to get a disc. So I need to find the volume of my disc. And again, we're going to say we have n discs, and I want to find the volume of the ith disc. Okay, not too bad. We know how to do this because we just did something very similar in the last section. Volume is just area times the thickness of the disk. In this case, since we sliced perpendicular to the x-axis, the thickness is delta x. Or if you want, you could look at this representative rectangle and you could say the width of the representative rectangle is delta x. So it's area times delta x. And here's my picture. Looks like this. The area of a disk is just the area of a circle, so that's pi r squared times delta x. It's pretty easy. Now our job is just to find that radius in terms of x, just like in the last section. I need this in terms of this variable. Once I have the volume in terms of that variable, then I'm good to go. We add them up, we take the limit as the number of pieces goes to infinity. That defines an integral, and then we evaluate the integral to find the volume of the whole thing. Okay, so how to find the radius. The way I find the radius is I look at my picture. I highly, highly recommend doing all this visualization. When you do this, you get the right radii. I find that students who don't do this, unless they're able to visualize all of this in their heads, they're not going to get the right radius because they're just trying to memorize things. The picture tells me everything I'm supposed to do. I need the radius. Now the radius always starts at the axis. So it starts at, here's our axis, y equals -1. And it goes out to the outermost point on the disk. Or alternatively, the radius is going to come from this representative rectangle. When I take that representative rectangle and I rotate it around, the diameter is the length of that representative rectangle plus the length of the representative rectangle. So the radius is actually just the length of the rectangle in the first place. So either way, you can think of it as the distance from the axis out to that outermost point on the disk, or the distance from the axis out to the outermost point on your representative rectangle. But it's the same thing. Like that representative rectangle rotates and gives us this disk. So it's not too bad. It's a vertical distance. Vertical distances are differences of y values. You're going to take the top y value and you're going to subtract the bottom y value. But I need those as functions of x. So the top y value as a function of x, well, that was actually given to us. That was given by the equation of this curve. That was y equals 2.5 plus sine of x. So our top y value is 2.5 plus sine of x, but I'm on the ith disk, so I'm picking out an x value on that ith subinterval. I'm going to call it x sub I. And then we're going to subtract the bottom y value. The bottom y value is just given by the equation of the axis. It's given by y equals -1. So I'm subtracting -1. So I end up with 2.5 minus a -1 is 3.5. So I end up with a radius of 3.5 plus sine of x sub I. That's my radius. It goes right there. All right. So the total volume is approximately the sum of all those volume pieces. And that's equal to the sum as I goes from 1 to n of the v sub I, and v sub I is right here. So that's pi times 3.5 plus sine of x sub I, quantity squared times delta x. And if I want the exact volume, I take the limit as the number of slices goes to infinity, or as delta x gets closer and closer to 0. And that is the definition of this integral. We have pi times 3.5 plus sine of x, quantity squared. Delta x becomes dx in the limit, and we integrate from x equals one number to x equals another number. To figure that out, we always look at the original region, forget about the reflection. X started at 0 and ended at 2 pi. So I'm going to integrate from 0 to 2 pi. And then we're going to get the volume of this solid. It's like a vase. Looks like a very wide vase. Okay, I've got a binomial squared. Derivative of sine of x is cosine of x. I don't have a cosine out here, so unfortunately can't do a u sub. So we're going to have to write that twice in FOIL and then evaluate the integral. So volume is pi times the integral from 0 to 2 pi of 3.5 plus sine of x times itself and I don't know what 3.5 times 3.5 is, but I know 3.5, isn't that 7 over 2? Well, 7 over 2 times 7 over 2 is going to be 49 over 4 plus outer times outer is 3.5 sine of x. Inner times inner is another 3.5 sine of x. So I've got 7 sines of x. And last times last is sine of x. Quantity squared, or if you prefer, sine squared x, same thing. All right, I've got a rule for that and a rule for that. Now sine squared x I do not have a rule for, but remember we've already studied trigonometric integrals. Well, if you're in my class, you've already studied trigonometric integrals. If I want sine squared x, I don't have a rule for that, but I've got a rule for all of the terms that come from my power reducing formula. Here's my power reducing formula. Sine squared of some angle is 1/2 of 1 minus cosine of twice the angle. Whatever the angle is. Just double the angle, put that in over here, and that's the same thing. And I've got a rule for that, and I've got a rule for that. So we're going to use that here. In this case, our angle is x, so we've got 1/2 of 1 minus cosine of 2x. And we can anti-differentiate that instead. Or you can distribute the 1/2 through. So 1/2 times 1 is, of course, 1/2. 1/2 times that negative cosine is negative 1/2 cosine. I could write that as 2 over 4 if we wanted. So we can add these two guys together. 2 over 4 plus 49 over 4 is 51 over 4. Okay, now I've got a rule for that, and a rule for that, and a rule for that. Easy breezy. Just apply our anti-differentiation rules. So we have 51 over 4. Antiderivative of a constant is your constant times the variable. Then I bring down my 7. The antiderivative of sine is negative cosine. Bring down the negative 1/2. Now this is a cosine of kx. The antiderivative of cosine of kx is sine of kx. So you replace the 2x back inside. Do not change your angle. Your angle is always going to stay the same. Now, if I were to take the derivative of this, I'd have to multiply by a 2, by the chain rule, right? If I'm taking the antiderivative, I have to divide by the 2, or multiply by 1/2, same thing. Okay, so that's our antiderivative. By the fundamental theorem, this value is equal to this evaluated at 2 pi minus this evaluated at 0. So I've got pi times 5 pi over 4 times 2 pi. Got minus 7 cosine of 2 pi minus 1/4 sine of 4 pi, and then we substitute in 0. So I've got minus pi times a constant times 0, which is 0, minus 7 cosine of 0 minus 1/4 sine of 0. And then if we remember our trig identities, we can simplify this real quick. Cosine and sine, or cosine of 2 pi is 1. Cosine of 0 is 1. Because it starts at 1, right? It starts at the top, and then it repeats every 2 pi. So this is 1 and that's 1. Sine of 0 is 0. It starts at 0. And it repeats every 2 pi too. So sine of 0 is 0, sine of 2 pi is 0, sine of 4 pi is 0. Okay. So this is our answer, just not simplified. I've got pi times 2 goes into 4 twice. 51 over 2 times pi minus 7 minus 0 minus pi times negative 7. So I end up with 51 over 2 times pi squared minus 7 pi plus 7 pi. The 7 pi's reduce. And we get 51 over 2 times pi squared. What was that again? It's volume. This is units cubed. And what was that again? It's the volume of this vase-looking thing that we just came up with. Okay, so that's finding a volume using the disc or washer method. Well, that's our first example. In the next videos, we're going to see some washers, and yeah, we're going to rotate around other axes. I want to show you discs, I want to show you washers, I want to show you rotating around axes on all the sides of our region. So here's our region here. We could rotate around a line that's below our region, or a line that's above our region, or a line that's to the right of our region, or a line that's to the left of our region. You can rotate around anything. Our textbook author likes to rotate around the X and Y axes. That's nice, but I want you to get comfortable rotating around a line that's on any side of your region, and then we'll see what happens. And we'll see how the formulas change as that axis changes, and as that region that we're rotating or revolving about axes either meets the axis, like this one, or doesn't meet the axis, like we'll see in the washer method problems. So that's for another video.